Hey, hello. Can you hear me? Ricardo.
Okay, so can I hear?
Yeah, can you hear me, Ricardo?
Okay, so can I be heard now? I think so.
You need when you are sharing screen, you need to share screen with the sound. There's a tick.
Šito, ta prasme, vat kažkiek apie ką jūs nenaudojat, nenaudosite. Ne, ir dar važinėkite, ir dar kitam kažką nekalbėti. Tada aš viskas susijungsiu. Gerai. Ir padarysim demonstraciją. Girdėti,
Is it working now?
tu.
Can I be heard? Excellent. I think I can be heard now. So starting again, thank you. I want to thank the organization for accepting my talk. I want to thank all of you for being present at this talk. And today we're going to talk a little bit about service meshes in general and Istio in particular. So what will we be covering today? So we'll be covering a little bit about microservices. So the idea of new microservice architectures and some of the challenges that microservices bring to the table. We're going to talk a little bit about service meshes in general and Istio in particular. And then we're going to see some of Istio's features to know traffic management, security, and observability. So on this first slide, I'm just showing off my amazing design skills, but you get the point what I'm trying to come to throw across here. So the idea is that in recent years we started to transition between a monolithic architecture into something more of what we know now about as microservice architecture. So the idea is that we are in an era of digital transformation, and we are in a pursuit to better serve our customers. And usually this means that we require faster development cycles as well as more and faster deploys. But why do we do this? So we have several advantages in using a microservices architecture and adopting this kind of approach. So some of those are described here. So we gain maintainability. So now we have a smaller scope in each of the microservices, so we can wrap our heads around of what the service really is and what are the goals that we want to achieve. And of course we gain some scalability. So now we have smaller independent services that we can scale independently and during about the needs that we have at that point. If done correctly, we also have loose coupling between those services. So it means that we can scale those services independently. It means that if one service goes down, the whole platform doesn't go down. But again, this needs to be done in a way that allows for this. As we mentioned before, we gain deployability independence, meaning that one microservice can be deployed independently, can be scaled and deployed independently. We can launch specific features on those kinds of services. We also can organize our business capabilities around those microservices. So some teams can own 2, 3, 4, or some of those microservices, and we can organize our companies around those kinds of services. And of course, we can have small team ownership. So now we don't have a big, huge monolith. We can have smaller teams that can own a fraction of the whole business capability. But is this all advantages? Of course not. So microservices is not a silver bullet, and it comes with its own challenges. So as we've seen before, we gain things like faster delivery, isolation, scaling. We can build our culture around microservices, and we also gain some flexibility. But now, instead of having a big application, we have a bunch of smaller applications that somehow need to communicate with each other. So that comes with its own sets of challenges. Some of those are described here. So now we have service discovery. This means that now we have services that are communicating with each other, and they need somehow to find each other in order to make requests and manipulate data. Of course, we also need to load balance traffic between those services. Now, so because we can have one service that, for example, has 2 replicas and one that has 100, and we need a way to actually load balance the traffic between the services to gain some flexibility. As we've seen before, we also need to be aware of fault tolerance. If we don't want one service to bring the whole platform down, we need to account for this kind of behaviors, or else we have something that is usually known as a distributed monolith. We also now have several services that are communicated with each other. So we don't have only one application that receives a request, does what it needs to do, and sends a response back. So we need some way of actually understanding when a request comes in, what happens within the platform. So it's something that can be tackled with distributed tracing, meaning that we need a way to understand when a request comes in, what are the services that are actually going to be touched, and what they are doing, how long is it taking. And that comes bundled, of course, with metrics. Now we have several services. We need metrics from the host and from all of those services to understand what they're doing on a particular basis. And of course, security. So now we have several services communicating with each other. So they need to authenticate themselves. They need to authorize themselves. And we need to pass authorization and an authentication down from service to service to make sure that a request from a user does what it is supposed and has the correct permissions. So what is a mesh network? So on a high level, a mesh network is a local network topology where nodes connect directly without the need for specialized nodes to perform certain tasks. This means that we don't have specific aggregate nodes that perform specific tasks. Nodes connect to each other directly and they cooperate. They can, of course, obtain information in order to make that organization from an external source, for example, but it means that we don't have particular nodes that will actually tackle specific tasks. So building on top of this, it comes the concept of a service mesh. The idea for a service mesh is to be the connective tissue between all of our services and to add additional capabilities like timeouts, retries, service discovery, load balancing, resilience, observability, and much more. A service mesh implementation will allow applications to offload these capabilities that we've just seen from the application level libraries to the service mesh itself, and allowing developers to only focus on business logic. Most service mesh implementations are built on top of two main concepts. The first one is the concept of a service proxy. So a service proxy will be a proxy from where all traffic will go in and out of the mesh itself. So it will act as an intermediary or interceptor that can add those capabilities that we've seen, like retries, timeout, circuit breaking, and service discovery. Another important concept is the concept of the sidecar. So a sidecar will be an application that will live alongside the main application, and it will have the same life cycle as the main application. This means that when the main application comes live, the sidecar will also come live, and when the main application goes down, the sidecar will also go down. The sidecar pattern is sometimes referred as the sidekick pattern, and it's known to be a decomposition pattern. On a high level, this is how most service mesh implementations look like. They are usually divided into two planes. The first one is the data plane, and there's where our applications live alongside the sidecar proxy. That sidecar proxy usually connects to something that is known as a control plane, either to send information or to pull information back for configuration. We usually interact with the service mesh via a CLI or an API in order to get some information or to configure, for example, the sidecar proxies to send information about the configuration for authentication or to connect to an external service. And of course, both the sidecar proxies and the service mesh control plane can send metrics to external services, can send traces to external services, meaning that they can communicate with external services. So what is Istio? So Istio provides a behavioral insights and operational control over a service mesh. The idea for Istio is to make it easy to create a network of deployed services with load balancing, service-to-service authentication, monitoring, and much more, with the ultimate goal of few or even no code changes to our services. The idea is for Istio to be right there alongside our applications, but our applications don't even need to be aware that Istio is there. That is achieved because we deploy a special sidecar proxy in our environments that will intercept all network communication between microservices, and we'll then configure Istio using its control plane functionality. Istio is also designed for extensibility and will meet a diverse deployment needs. So building on the architecture that we've seen before, this is more or less what Istio looks like. So it's very similar to the architecture that we've seen before. So we have the two planes, the data plane and the control plane. On the data plane, we have our services and we have the sidecar proxy. In Istio land, the sidecar proxy is implemented with the use of Envoy. On the side, the control plane, we have Istio that has a bunch of services that each of them have their own responsibilities. So Envoy is a high-performance proxy that was developed at Lyft, and its idea is to manage all inbound and outbound traffic for the services on our service mesh. Again, it's deployed as a sidecar proxy and alongside the relevant services that will be deployed in Kubernetes with pods. This will allow Istio to extract a wealth of signals about traffic behavior and attributes. And of course, those sidecar proxies can enforce policy decisions and send information to monitoring systems to provide information. The sidecar proxy model will allow us to add Istio capabilities to an existing deployment with no need to re-architecture or rewrite code. Istio is Istio control plane. It will provide service discovery, configuration, and certificate management. The idea for Istio is to convert high-level rules into something that Envoy can understand. We can interact with Istio via its management API. It possesses security features for service to service and end-user authentication and authorization. And it can also act as a certificate authority and generate certificates for mutual TLS. So now we're going to see some of Istio's features, and we're going to start with traffic management. So traffic management usually means traffic rules to control traffic between services. The idea is to make our lives easier and to offload capabilities like timeout, retry, circuit breaking, canary rollouts, A/B tests, all to the service mesh itself. These are patterns that big companies like Amazon, Facebook, Netflix, just to mention a few, use on a daily basis. Also, Istio's out-of-the-box failure recovery features will allow our services to be more robust against failures of dependent services or even the network. So now we're going to see several concepts of traffic management within Istio and how they are implemented. We're going to touch some things like virtual services, gateway services, service centers, and a bit more. So the first concept that we're going to see in Istio is the concept of the virtual service. So what is a virtual services? Virtual services is how requests are routed to a service within the service mesh itself. They are a set of rules that are evaluated in order from top to bottom, and that will allow Istio to match each given request to its real destination. Looking at this particular example, we can see that we have three sections. So the first section is the host section, and these are user addressable destinations. These are the addresses that the client will use when it sends a request to a particular service. Next, we have the HTTP section, and those are the virtual services routing rules. And they describe match conditions and actions for the routing itself. A routing rule will consist of a destination where we want to send the traffic to and 0 or more match conditions depending on use case. So in this example, in the first routing rule, we have a condition, and so it will begin with the match field. In this particular case, we want this routing to apply to all requests that come from the user MCC Ricardo. So we use a header which is named end user and the exact field to select the appropriate requests. And the last point is the route field, which specifies the actual destination for the traffic that matches that particular condition. And it has to be a real destination that exists in Istio service registry, or the Envoy proxies won't know where to send the traffic to. And of course, we can have default rules for all the requests that don't match any rule. We can also have multiple match conditions or multiple match blocks to make it as complex as we require. We can also distribute traffic by percentage of weight. So in this example, we're saying that for the destination of block V1, we're sending 75% of the traffic, and the remaining 25 will be sent to block V2. We can also use routing rules to perform some actions on the traffic itself. For example, we can append or remove headers, or we can rewrite a URL. The next concept that we're going to see is the concept of the destination rule. So we can think of virtual services as the way that we route our traffic to a given destination. And the destination rule will be what happens to the traffic for that specific destination. Destination rules will be applied after the virtual service routing rules are evaluated. So it means that they will be applied to the real destination. We use destination rules, for example, to specify named service subsets for those to be used inside of virtual rules. We also on the destination rule, we can configure load balancing for each of the destinations. By default, load balancing will be round robin, but we can also configure random, weighted, or least requests. Each subset will be based on one or more labels, which in the Kubernetes world will be key value pairs that be attached to objects, for example, pods. Looking at this example, we have configured a random load balancer for version V1 and V3. And for version V2, we have a specific round-robin load balancer. The next concept is the concept of a gateway. And gateways are used to manage inbound and outbound traffic to the mesh. They are applied to standalone proxies that run on the edge of the mesh itself. So those will not be the Envoy proxies that live alongside the application. They are primarily used to manage ingress traffic into the service mesh, but can also be used to manage egress traffic. They will let us configure dedicated exit nodes for traffic leaving the mesh, limiting which services can or even should access external networks, or even to enable more secure control of egress traffic. So in this example, we're allowing HTTP traffic from mccricardo.com into the mesh on port 443, but we don't really apply any routing rules to the traffic. To specify routing and for the gateway to work as intended, we must also bind the gateway to a virtual service, like virtual services we've seen before. And we will do this by using the virtual services gateway field. We can then use virtual service with the configuration we've seen before and make them as complex as we require. Another important concept and very useful concept is the concept of the service entry. And a service entry is used to add an entry to the service registry that Istio maintains internally. This means that after we add a service entry, the Envoy proxies can send traffic to the service as if it was part of the mesh itself. Configuring service entries will allow us to manage traffic for services that run outside the mesh, but we can treat them as if they were part of the mesh itself. And this means that we can use the same concepts that we've seen before. We can configure timeouts, we can configure retries, we can configure fault injection, and much more. We can also add services from different clusters to the mesh and configure multi-cluster Istio meshes on Kubernetes. We don't actually need to add service entries for every external service that we want our mesh edge to connect to, because by default, Istio configures the Envoy proxies to pass through requests to unknown services. However, we can't use Istio features to control traffic for those destinations since they aren't registered within the mesh. So in this particular example, we have a destination rule configured, which is enforcing mutual TLS to a service that is defined as a service entry. And of course, something that we've mentioned many times before, we have the usual network resiliency features built in Istio. So in the example on the left, we are, for example, stating that we want a 10-second timeout to a destination of the block. In the middle section, we are configuring retries, and we are saying that we want, if something fails, we want to retry it 3 times, and we want to wait 2 seconds between each retry. And on the right, we have an example of of circuit breaking, where we are saying that we are allowing a maximum of 100 connections into the block. And last but not least, we come to fault injection. So in the last few years, chaos engineering has become more prevalent, and Istio allows us support to add failure injection capabilities and make them in an easier way. And we can inject failures of 2 types in Istio, both in the virtual service. We can inject delays, which are usually timing failures, and they mimic increased network latency and an overload to an upstream service. We can also add aborts, which usually mean crash failures, and they mimic a failure on an upstream service, and they usually manifest themselves in the form of an HTTP error or TCP connection failures. So in this example, we're saying that we are injecting a 5-second delay for 10% of the requests that go into destination block. This is a nice way to actually gain trust in our systems and to test that our network resilience capabilities actually work, the timeouts are working, the retries are working. Now we're going to touch a little bit on security that Istio provides out of the box. So when we break down a monolith into microservices, that comes with several benefits. Like we've seen before, we gain better agility, better scalability, and better ability to reuse services. However, as we've seen, microservices also have particular needs, and some of those are security related. So we need to defend against man-in-the-middle attacks, and that usually means traffic encryption. We also need to provide flexible service access control, and that usually means mutual TLS and fine-grained access policies. We also need to determine who did what and in what time, so we need auditing tools. The idea for Istio security is to provide a comprehensive security solution to solve this kind of issues. In particular, Istio security will mitigate both inside and outside threats against our data, endpoints, communication, and platform. The Istio security features will provide strong identity, powerful policies, transparent TLS encryption, authentication, authorization, and auditing tools to both protect our service and our data. On a high level, this is how Istio security works. So Istio security involves multiple components. It will have a certificate authority, for key, and certificate management. It also will have a configuration API, which will allow us to distribute information to the proxies. Some of that information will be authentication policies, authorization policies, and secure naming information. The sidecar and perimeter proxies will work as policy enforcement points to secure communication between clients and servers. And a set of Envoy proxies extensions will allow us to manage telemetry and auditing capabilities. The control plane will handle the configuration from the API server and will configure those policy enforcement points into the data plane. And those policy enforcement points will be implemented using Envoy proxies. So now we're going to touch a little bit on authentication and authorization. Istio provides two types of authentication. To know, they are peer authentication and request authentication. Peer authentication will be used for service-to-service authentication to verify a client that is making a connection. Out of the box, Istio offers mutual TLS as a full-stack solution for transport authentication, which can be enabled without requiring any service code changes. Request authorization will be used for end-user authentication to verify the credential attached to a request. Istio enables request-level authentication with JSON Web Token validation and a streamlined developer experience using custom authentication providers or any OpenID Connect providers. In all cases, Istio stores the authentication policies in the Istio config services store via the Kubernetes API, and Istio will keep them up to date for each proxy along keys where necessary. And a very interesting feature is that Istio supports authentication in permissive mode that will help us understand how a policy would change and affect our security posture before it is even enforced. So now we're going to see an example of a peer authentication and request authentication. So Istio tunnels service-to-service communication through the client and server policy enforcement points, which will be implemented as Envoy proxies. Mutual TLS has a permissive mode, which allow us service to accept both plain text and mutual TLS traffic at the same time. This feature greatly improves the mutual TLS onboarding experience. In this example of authentication policy, we're specifying that the transport authentication for workloads that have the labels app, blog must use TLS. Request authentication defines what a request authentication method are supported by a workload. It will reject a request if the request contains any valid authentication information based on the configuration authentication rules. A request that doesn't contain authentication credentials will be accepted, but will not have an authentication identity. And to restrict access to authenticated requests only, this should be accompanied by an authorization rule. So in this example, we're requiring a JSON Web Token for all requests for workloads that have app label block. Next, we'll touch briefly on authorization. And Istio authorization features provide mesh, namespace, and workload-wide access control for workloads in the mesh. Their authorization policy will enforce access control to all inbound traffic in the server side of the Envoy proxies. Each Envoy proxy will run an authorization engine that will authorize requests in runtime. We don't need to explicitly enable Istio authorization rules. We just need to apply an authorization rule for all the workloads that enforce access control. For workloads without authorization policies applied, Istio will not enforce any access control, allowing all requests. We're now going to see a few examples of authorization policies in practice. So in this example, this policy allows traffic only from the workspace, the namespace development. In other words, we are isolating namespace development from all other namespaces. This feature requires MTLS to be enabled. So let's imagine that we have configured peer authentication to strict, but we really want to make sure that traffic is indeed protected by mutual TLS with an extra check in the authorization layer. This is also known as defense in depth. This example policy denies any request if the principal is empty. And the principal will be empty if plain text is used. So in other words, the policy allows requests if the principal is non-empty. And the asterisk means that non-empty match, and using not principals means that matching on any non-empty principal. And last but not least, we have an example of JWT validation. And it's common in ingress gateways, and we might require different JWT issues for different hosts. We can use the authorization policy for fine-grained JWT validation in addition to the request authentication policy. Using the following policy, we want to allow access to a given host if the JWT principal match. Access to other hosts will always be denied. Now we come to the last topic, and it will be the topic of observability. So Istio generates the following types of telemetry in order to provide an overall idea of the observability to the mesh itself. So Istio provides metrics, which means that it generates a set of service metrics that are based on the 4 golden signals of monitoring. And those are latency, traffic, errors, and saturation. Istio also provides detailed metrics for the mesh control plane. Istio also provides the concept of distributed traces. And this means that Istio will generate distributed trace spans for each services, providing operators with a detailed understanding of the call flows and service dependence within the mesh. And of course, Istio provides access logs as a way to actually understand what is happening on each of our services. So metrics are a way of monitoring and understanding behavior in aggregate. So to monitor service behavior, Istio generates for all traffic, both in and out of the mesh, a rich set of service metrics. These metrics will provide information on behaviors such as the overall volume of traffic, error rates, and response time, for example. In addition to monitoring behavior of the service within the mesh, Istio also provides information of the mesh itself and provides metrics on those. Istio's metric collection will begin at the sidecar proxies, which are known to be the proxy level metrics. Each proxy will generate a rich set of metrics about all the traffic coming in and out of the service itself. The proxy will also provide detailed information about the proxy itself so that we can monitor its health. Istio provides a set of service-oriented metrics for monitoring service communications. These metrics will cover the 4 golden signals that we've seen before. And of course, the Istio control plane also provides a set of metrics that will allow us to monitor the overall health of the mesh itself. Another important concept is the concept of distributed traces. So distributed tracing provides a way to monitor and understand the behavior by monitoring individual requests as they flow through the mesh. This feature will allow service mesh operators to actually understand the service dependencies and the sources of latency within the mesh. Istio supports distributed tracing through the Envoy proxies, because those proxies will automatically generate spans on behalf of the applications they proxy, and they will only require that the applications forward the appropriate context. Istio supports a number of tracing backends, and those include Zipkin, Jaeger, Lightstep, and Datadog, for example. Operators are left to control the sampling rate for trace generation. This means the rate at which tracing data is generated for each request. This allows operators to control the amount of rate of tracing data being produced in the mesh. In this example, we're seeing an example of tracing data for a request, and is being shown with Zipkin. And last but not least, we have logs. So access logs provide a way to monitor and understand behavior from the perspective of an individual workload instance. Istio can generate logs for service traffic in a configurable set of formats, and provides operators with full control on how, what, and when of the logging. And Istio can do much more. As we've seen, we've covered some of the basic tasks that Istio can cover, but Istio has a lot more features that we don't have time to go into detail here. So Istio supports multi-cluster meshes, it supports WebAssembly extension, it supports request classification. It has a lot more features that are worth delving into and exploring a little bit more. One of the good things with Istio is that we can onboard these features as we require within our services. And this is it from my end. I hope this presentation was informative for all of you. I hope it gave you a broad idea of some of the main features that we can onboard with Istio and how it can help operators on a day-to-day basis. Thank you very much. And if you have any questions, please just shoot.